speeddeciphers.org. My name is Cordelia Kataria, and I am a 9-year-old computing explorer and problem solver. Today we're going to be solving a Hackerrank problem, and it's called Find the Running Median. So what the problem says is that the median of a set of integers is the midpoint value of the dataset for which an equal number of integers are less than and greater than the value. To find the median, you must first sort your self-integers in non-decreasing order, and then if your set contains an odd number, the median is the middle element. So for example, if it's 1, 2, 3, 2 is the median. If it contains even, then it's the average of the middle elements. Then for 1, 2, 3, 4, 2 plus 3 divided by 2, that's 2.5, which is the median. So given an input stream of n integers, perform the following task for each ith integer. Add the ith integer to a running list of integers. Find the median of the updated list. So for the first element through the ith element. Print the updated median on a new list. The printed value must be a double position number scaled to 1 decimal place. So for example, 12.3 format. So then each of the median values is stored in an array, and the array is returned for the main function to print. Note, add formatting to the print statement. Function description. Complete the running median function in the editor below. Running median has the following parameters. Int a of n, that's an array of integers, and it returns float of n, that's the median of the array after each insertion, and modify the print statement in main to get proper formatting. So the first line contains a single integer n and the number of integers in the data stream. Each line I of the n subsequent lines contains an integer a of I to be inserted into the list. So the constraints are between 1 and 10 to the power of 5, that's n, and a of I is between 0 and 10 to the power of 5. And then sample input is the actual input is 6, 12, 4, 5, 3, 8, 7. Then the output is so what the function is, so there's an A with size n, which is 6 for this one, we know that, and then for 12, you know that A is 12. Over here we also add 4, and then 5, and then 3, and then 8, and then 7, so we get the array of that. And the output of this is 12.0, 8.0, 5.0, 4.5, 5.0, and 6.0. And that's because there are 6 integers, so we need to print the new median on a new line as each integer is added to the list. So then list is 12, that's 12.0, and then the next iteration 8, the next one is 5, next one is 4.5, the next one is 5 again, and the one after that is 6.0. Right, so we have to solve this equation. So we have to solve that problem. Right, 1 second, just working out. Then to do that, in a second, it's not working. There we go. Then to solve this problem, what the problem says is that we have a stream of integers, basically. Then let's say something like 2, then 3. Insert 2, 3, then 1, 5, 7. Right, so and then it's a stream. So we have so you need to insert that, insert that, insert that, insert that, and insert that. And then what we have to do is to keep finding the median at each thing. So then that's then the median over here. The element is just 2, so then do in, and then there's only a 2 element, and then now we have 2 and 3, then 2.5, and then 1, 2 and 3, so then that is 2 median again, and then if we have 5, then 1, 2, 3 and 5, that's 11, and 11 divided by 2, that's 5.5. And then if we add
no. Your set is 1, 2, 3, 5. Medium is 2.5, not 5.5.
Because it's not divided by
Medium is the average of the middle elements, right?
Yeah, I think I accidentally divided by 2. And that is the that's the not the median, it's the mean, and it would be the mean if I divide by 4. I mean, but didn't. So for 1, 2, 3, 5, 7, then that's 3.
Right.
Then that's the input and output of that. So if we could make some basic codes, and let's say A is not A because that's already in use. Maybe answers that for I in A, and the ans dot then also, and I just call it C. Alright, so not ans, so C of A. So I'm actually going to do so we could do ways then that in good approach 1, then every element, so add every element in a loop and each iteration we sort it, and so in each iteration we sort it and get middle value. Okay, so then if we compute the time complexity of that, so it's sorting, that's n log n, then every element add, that's order, that loop is order of n, where n is the length of a, and then for the sorting, that's about n log n, because then it's n times n log n, which is order of n squared log n.
Continue here, just a trivia thing. So here, your element will be in the worst case. Let's say this is your sorted list, and your element is added at the start. So let's say AI is added here, and this part is all sorted. So in the worst case, it will just take this element like O(n) time to reach the end. So just for this problem, you can say that sorting will take O(n) time, like just a small trivial thing. But yeah, in general, sorting takes n log n time.
Yeah, okay, so we can say that that's about order of n squared.
Right.
Okay. Then so we could optimize on this by optimization by instead of every iteration completely sorting it, we can just insert the element, because the whole array is already sorted, so we just need to insert that element. So we can use the insert process of insertion sort. So if we've got like an array we've got 1, 2, 3, 5, and we want to add 4, then let's compare against the first one. Then so 4 is more than 1, 4 is more than 2, 4 is more than 3, but then 4 is less than 5. So 4 is less than 5, so that means it needs to be just before 5. Then it's 1, 2, 3, 4, and 5. But that's still around order of. But I won't optimize it much because it's just because sorting, it just takes about order of n. So then that's about the same time complexity as the insertion process. So it's not much of an optimization, but it's still.
Right.
So for this thingy, n is 10 to the power of 5. 10 to the power of 5 squared, that's 10 to the power of 10, and 10 to the power of 10 is just way too much. So I'm pretty sure we need to optimize it further.
Right.
So first let's look more closely at the example of 23157. Then we have 2, 3, 1, 5, and 7. Next then so yes, for that thing we have 2, and then the median is 2, and we get 2 and 3. The median is 2.5, then it's 1, 2, 3. And I'm going to do just 1, 2, 3 and 2, 3, 1. Then merge is 2 again, and then 5 is, actually I'm not going to do that. Then 1, 2, 3, 5. Then the median for that is 2.5. Then 4, 1, 2, 3, 5, 7. The median is 3. Right, so if we look at the 1 or 2 elements that provided the median, you can see that yes, it's that one, those 2, that one, those 2, and that one. So yeah, it's either the middle one or the 2 middle ones. And middle, that's just, I guess that's just halfway through it. So I think if we just we look, I think that means we just need to keep track of those 2 elements, but
Going in the right direction.
But I think if we keep track of just those elements, then it's inserting things will be a bit hard. So I think
So what will be the so let's break what we do is let's break this array into 2 parts. Let's take this example and break the array of length 4 into 2 parts. So what can you say about this number, like the number just on the left? It must be the greatest number in the left array, right?
yeah, and it's also one of the useful elements.
Right. And this number is also one of the useful elements, and it is the smallest number on the right.
Yeah.
So now can you try something from this?
Right, so yes, so I think that means that we can keep track of the two halves thing because 1 second. There we go. We can keep track of the two halves. Then it's just the greatest element of the first half and the smallest element of the second half. So H2. I don't think arrays will work well for it because then we need to insert it and then that's order of n squared again. So we need a data structure so that we need a data structure so that we can easily know the maximum or the minimum element. So I think we can use a heap because then if we use that example, then heap 1. I'm just going to do a bit of a run of it. Heap 2. That's that.
So this one gives us the max element. So this is a max heap.
Yeah.
And this one gives the minimum elements. Yeah. So this is the min heap.
Yeah. Then yes. So, and we need to add 2. Then if we add this, I think so if we add 2, then I think we can I think we can add it on any one of them. I think because there's no elements in there, so then let's add it on the smaller one. And then when we add on 3, then heap 2. So we add on 3, then I think it needs to go over here because it's greater than the greatest element in heap 1. And then when we add a 1, and that's appended to heap 1 because so do that, and then that's the 3, and heap 1. I think we add a 5 now, then that stays the same.
So how do we know which heap to add the element to?
I think it's just so I'm pretty sure we have to find I think we have to find the middle of the greatest element in heap 1 and the smallest one in heap 2, because that's basically like the middle of everything. And if it's less than that, then I think it goes to heap 1. If it's more than heap 2,
So an easier way to do this is, let's say you want to insert 5 here. So what you can do is just here the length of heap 1 is 2, right?
Yeah.
And the length of heap 2 is 1.
Yeah.
So what you can do is you can add 5 to heap 1 first. So length of heap 1 becomes 3, which is 2 more than size of heap 2. So then when there is a difference of 2 elements, you pop the largest element from heap 1 and push it to heap 2.
Okay.
So that also resolves the problem.
Okay. And so then it's back on 5. Then let's just add the last element now. 1, 2, that's 7. Heap 2 is 3, 5, 7. So if we find the median, then for the first one it's just none.
Okay, we need to take it from the middle only. I think, yeah, you were right. I was wrong. Yeah, sorry.
It's then for that one's, I'm pretty sure if the second T is I think if the if one of them is greater length than the other, then I think we can just do so if one is greater than the other, then if one heap is greater than the other, then just do the largest or smallest element of that heap. So then I think it was then, because then it will work for this one, and then for that, so the next one 2.5, this one middle of 2, and wait, actually that's just 2 because 1 is bigger. Wait, 1 second, got to move that. Okay, so zoom in a bit. That one's just 2, and then this one is same length, so middle of 2 and 3, 2.5. Then for the last test case, 1, 2, and 3, 5, 7. So 3, 5, 7 is the bigger heap. So I guess it is 3. And I'm pretty sure that was the actual answer, 2, 2.5, 2, 2.53. And the answer is 2, 2.5, 2, 2.53. Okay? So we got it right, I guess.
Right. So we can start coding it.
Yeah, pretty sure. So let's move to coding. Wait, I mean the question. It's then for the I just 1 second, just was trying to set then. Okay, so then for this it was, so we need 2 heaps, then you have to import heap q. So heap q, A is that. I don't know if it's then, wait, no, not A1. A1.
So you don't have to heapify it at the start, right?
Okay. I'm just not sure if heap q does anything to empty list, so that's why I do it.
Heap to dot heapify converts a list into a heap.
Yeah, I know. But I'm not sure if it changes anything to the empty list. Right.
Yeah, it won't change anything to the empty list.
And for I know. Then A1 dot heap q dot
You need to see to
dot heap
make 2 heap.
and H, wait, I just got it H1 and H2 for half 1, half 2, and also for heap 1 and heap 2. Heap q dot heap push of H1, comma, wait, first we need to check the smallest ones, then heap H1 of 0. Now that would be smallest one. Wait. I don't think there is an implementation of a max heap in Python, so I think we're just going to have to use negative values in the second heap.
Right.
So for H1,
We'll have to handle it a little more carefully.
yeah. So if len of H1 is less than len of H2, it is minus that is, actually I'm just gonna do that. Then
So you need to compare the middle element, right, to see where the IE will go,
but
not by the length.
I'm right now I guess
If the length goes beyond 2, then you can switch up, like you can then check the length.
um so so right now let's do the so if H1 of 0, if H1 of 0 is more than is plus H2 of 0, divided by if not H1 and not H2, and not divided by divide, just divide by. If not that, then hate, and just if there's no heap, I think we can just add on anyone. Dot append I. Wait, no, not append. Heap q dot heap push. Heap q dot heap push off I.
If it's a single element list, both these operations are same, but fine. We can use heap q dot heap push everywhere.
Then big I. Not a H1. And if not H1, then heap push off. So if left H1, heap q dot heap push off I think H2 comma I, left not H2, then off H4. Wait, that's H2 and that's H1, I think. If H1 is 0 plus H2 of 0 divided by 2, if
This might go a little wrong, Kotila. If you have 2 and then 1, what will happen here? You will push 2 to the first half, then you will push 1 to the second half.
I guess
So what you can do, go on.
I think what we can do is that if one heap is 2 or more than it has a length of 2 or more than the other heap, then just pop the smallest element and then just
Yeah, we can do that, but first we need to push the element in the correct half, I think. So let's assume like both of these heaps are empty. So we just push the first element into the first heap. That is fine, right? So if not h1, then we do heap q dot push h1 comma I. If h2 is empty, like the second element comes, so one of the two elements should go, like the bigger element of these two should go to h2, right?
Yes.
So we can write if like else if not h2, then heap 1 dot push, and then we pop the element from heap 1 and push it to heap 2. That will resolve our issue.
So heap push is using heap push pop off wait, not H2, H1 comma I. And wait, I think push pop that does the smallest and we want the biggest. then think second, then yes, we can do heat push off that, and then H1 off. I'm not sure how to get.
We can take out the first element. We can take out the biggest element from the first heap and push it to the second heap.
Yes, I guess it's only length 2, so I guess it will be. It won't be too inefficient. So I guess we can do that.
Mm.
Q dot heap. We have to first remove the maximum one. Heap pop max. Then heap pop max. Yes, we can do that. Then E with that. That's the element. And then heap Q dot heap push off H2 and E, and we just do the same thing as that.
So heap like H1 is a max heap, right?
Yeah.
So everywhere you're writing anything related to H1, it should have a max function like heap pop max or heap push max, something like that.
So what I was doing is just what I was thinking of doing is just adding negative elements in H2s and I think we need to change like some operations. So like you can do this instead of that, we can do that.
Mm. Also, we need to do H1 over here. So on line 27, it should be heap push max as well.
I don't think there is a heat push max.
Just write it down.
HQ dot heat push underscore.
When you write underscore, you'll get the max. one.
It's not coming up.
Just write heap push once. Remove the underscores.
Okay, sorry.
I'm pretty sure you should get that. Heap push.
It's not there.
Remove H, remove S. Something in that.
Remove a what?
Just remove push.
I'm going to keep there. Looking for a heap push. These are the only ones over here.
Yeah, so I think we need to use a map. Like we'll use negative elements here then I think.
Yeah.
There should be a heap push max. Let me check.
I'll just in that tape part there.
Yeah, we need to use a negative element only.
Yes. Then then we do that, and otherwise if h1 of 0 plus h2 of 0 by 2, and that is if that if it's less than that. So if I is less than that, then heap q dot heap push off. Then if I is less than that, that means it has to be in h1, and then do h1 and
The first heap is the min. Sorry, the max heap, right?
what heap?
The first heap is the max heap, right?
Oh,
So all the operations will have negative. Yeah.
that one's not a heap, and that's a negative. Heap q dot heap push off, and that's a negative. Heap push
On line 27, you need to write heap q dot heap push.
27.
You have written only heap q dot heap.
Then
Also on line 21, it needs to be negative y.
there we go. And yeah, I think that's all of them. Then
So just a minor thing. On line 20, you check if not h1 and not h2. So you do that. So and on line 22, you're checking if not h1. So if there's no h1 line, it will go into line 21 already. So line 22 condition is like redundant. You can remove that. Like line 22, 23, 24, 25 are redundant.
If both of them are empty, then it goes in here. If just h1 is empty, then it goes in here. Not because it's that
if both of them are empty, then it will go in the first array, right? So the first array is always full, not full, but has at least one element. So
Right, so yes, we can remove that. But I think let's keep it here just to make sure that make sure
okay,
that
sure.
works. Then I want to just take you to heat push off that, and then if I have more than that. H2, I think we can change that to else.
Yeah.
Right, and yes, I think that's the insert operation done. Then to find the median, it's just
So one of the heaps can become like more than two length greater. So we need to handle that here.
then if none of H1 is more than is more than len of H2 plus 1, then
Plus two. Oh, no, plus one. Yeah. Then we can like pop one element from H1 and put it into H2.
Yeah, then pop H. So we should pop heap Q dot heap pop of H1 and put in H2. So heap Q dot heap push off H2 comma negative. Wait, no, not negative. Wait, yes, negative. Okay. I also think that should be just heap pop off H2.
Yeah.
And otherwise we just do the same thing. I mean, if it's if len of H2, that's len of H1, it's then it's
So take out an element from H2 and put it into H1.
wait, that's the wrong way. It's that, I think then that's done, and let's think. So now I think we can do the median. And also an answer equals that. if we're supposed to return a list or a, I think we're supposed to return.
Yeah, we need to return a list only.
Okay, let's try it out.
So, Cordelia, if there is an odd number of elements, what do you have to do?
If there's
Like the line you've written only stands for the even elements.
if there's an odd number of elements, in what thing, in what condition?
So, line 40 just stands for even number of elements, right?
Yeah, I guess
So, you need to put a few conditions there.
then if len of h1 is len of h2, if they're the same length, then we have to do that. Right, and then otherwise, if len of h1 is max of len of h1, comma, and if len of h1 is more than len h2, then answer dot end of h1 0. And if len of h2 is more than len of h1, answer dot append h2 of 0. It's then
And handling the negative part of H1.
If what it's just that. Right. I think we can run it again. Right. Wrong answer. 1.0, 1.5. We got minus.
So, you need to print out the decimals.
But I'm pretty sure that I don't think we need to do that. So, as it says for the second one, it says -1, but it's supposed to be 1.5.
First, let's do the decimal part, then we can see the exact issue.
Yeah, I think
Just convert all the integers to floating point values,
okay.
like in the input only.
And input just a append off, float off that.
Yeah. Also, when you divide H1 like H10 plus H20, you are doing floor division there. I think it should be integer division only.
What?
Line 41. It should be integer division. It should be like you shouldn't do floor division there. It should be normal integer division there.
I think. I think that should be normal division too. And
okay, go a little up. There must be an issue with the negative handling. Yeah, see, on line 29, it should be minus of E, or like line 30.
minus E. Wait. Yeah. Thanks. I think this one will work. Why does that button turn so right? Yay, we got it right. Yeah. Let's try and submit it. Yay! Yeah,
Did it get accepted?
Yeah.
Oh, cool.
Hey, wait, how many points
Cool,
did I
cool,
get?
cool.
Okay. 1390.95 and icing was max score is 50. Guess I got 50 points then. So we have finished the question. Now